There we go. This is the part that I think we're live here. All right. So folks, this part is a continuation. And here's my plan. Here's my plan today. So continue the discussion about definite integrals. And I'm going to finish that discussion today. And then we're gonna discuss some examples. We're gonna discuss some of the properties of the definite integrals. So the limit that we left out there last time as the definition, that's not gonna be something that we will use further on. So we'll use a different approach to calculate it. And then we'll get to the fundamental theorem of calculus. So that's kind of our projected path, and we're going to achieve these goals essentially Tuesday. We're going to end up finishing up the fundamental theorem of calculus. Hopefully, enough examples by Tuesday, so that we can then move on to some applications. And that's going to be essentially the remaining of a semester. So we have once we finish up Tuesday, I predict let's say next week will be last week when we cover new stuff. Then there's going to be applications. So the rest of the semester applications. And we also have a couple of tests left. So a quiz and a test. Quiz coming up next Friday. Test not this Friday, next Friday. So the test coming up in 3 weeks essentially. All right. So we're still at 4.2, folks. Section 4.2. For whatever reason, this is kind of leaking this ink. The definite integral. All right. So here's what we do, folks. For the definite integral, the limit that we learned yesterday. So remember, we had a function like this one. All right, so we had a function like this one. Let me just draw this thing away from here. So all right, there's a function here, and we have a point A and a point B. And we said if we want to estimate the area under the graph, right? We said yesterday. Then what we do, we divide this area, we divide this interval from A to B with a very fine subdivision, and then we build up rectangles that, one of their corners, for example, touches the graph. So, you have rectangles like this, and there we go, there's my rectangle. And there's another rectangle. There we go. So let's say one of the corners touches the graph. Now it doesn't matter which one of them. And we said if you want, you can allow these rectangles to go a little bit outside as long as the top side touches the graph somewhere. It could be in the middle. It could be to the side. There's a corner or something like that. So the sum of these areas, of these rectangular areas, is called the Riemann sum. And yesterday we said that we defined the integral from A to B of f of x dx to be the limit as n goes to infinity of the Riemann sums associated with and subdivisions. I'm not going to write what these are. These Riemann sums are. They were sums of things like this, f of x star times xi plus 1 minus xi or something like that. It's not that relevant. So it's the areas here. So what's relevant to us, and we can forget here about these things in a second. So what's relevant for us, I'm saying here, is that, this function f might turn out to be positive on some parts, and then negative on some other part. So in other words, my function f might turn out to be something like this. So if it's only above the x-axis, like in this example, the integral from a to b of f of x dx simply represents the area under the graph of f for a less than or equal to x less than or equal to b. So it represents this area. But that's only if f is greater than or equal to 0. In other words, f is above the x-axis. So the x-axis would be this one here. However, if f has parts above and below the x-axis, you can actually check, and this sum still makes sense. However, in that case, you will split up. Let's say the interval is from here. This would be A, and this would be B someplace here. So you get this area, and you also have this area. And this is B over here, folks. And I told you A is over here. So let's delete them from down here and put them there. So folks, what we're doing here when we calculate the integral from a to b of f of x dx, I'm going to say, you know what? Let's split it up here where there's a point C where the graph crosses the x-axis, and I'll say, let's split it up as an integral from a to c. Notice how I put the lower number lower here, the leftmost number to the lower here, and the rightmost number upper here. Likewise here, a to c, right? The same logic, the leftmost number at the bottom, the rightmost number at the top of f of x dx, plus an integral from c to b of f of x dx. And now these two, now why would it make sense to say that? It would make sense to say that because when I write these Riemann sums, you know, I can split up the Riemann sums in Riemann sums that go over here up to here, and then Riemann sums that go on the other side. So the ones that are below and the ones that are above. So it makes sense to split it up that way. And when we take the limits, you know, the limits and the sums have no problem commuting with each other. So at least when you have finite sums. So in this case, you have just two sums. So these are both infinite limits, but you know, they split up nicely. And I can say here, well, the first part is the area under the graph of f. You know what, let's make this bigger. Under the graph of f is a less than or equal to x less than or equal to c. And over here, area under the graph of f, where c is less than or equal to x less than or equal to b. And now, am I correct here actually in the second half? No, I'm not correct. So there's no such a thing as area under the graph of f. So I'm going to say here, area above. I'm going to replace the word under with above. So so this would be above the graph of f. So this area over here, folks, the one that I'm going to color now with red actually. So oops, it didn't work. All right, come on, red. There we go. So there's red here. So this area is the area below, is the area below the x-axis and above the graph of f. And I'm going to do the blue area. This is the blue area. This is the area above the x-axis and below the graph of f. So, so this one, folks, will come with a plus, and the other one will come with a minus. When you calculate the areas, this is going to be a positive number, and this one here is going to be a negative number. So in practice, this is what this integral represents. It represents an area, but you got to be careful. Again, it's an oriented area where it counts the areas above the x-axis under the graph of f with a positive sign, and it counts the areas below the x-axis, above the graph of f, it counts them with a negative sign. So that's the whole thing. Now that leads us to a natural question. Okay, so let's say we have something that is relatively symmetric, like the graph of sine, which it's similar to the one that I represented here. So let's say, you know what, the graph of sine, yeah, so it goes like this. Let's say we have that. You know, this area here and this area here, it's obvious that they're symmetric, right? One of them is with a plus sign and the other one is with a minus sign. Wouldn't they cancel when we add them up? The answer is yes, they would cancel. Yeah, they will cancel. So it's possible that the integral from a to b is 0 if, folks, the areas that live above the x-axis and the areas that live below the x-axis cancel each other out. So, so this integral is, again, is not necessarily the area, it's a signed area, and it could turn out to be 0. That's what you should all understand. And the remaining part of the hour, I'm going to do some properties of this integral. This is called the definite integral, by the way. When you have something like this, integral from a to b of f of x dx, and more or less like, if you remember, folks, when we talked about derivatives, we said derivatives, you know, intuitively, what are those derivatives? Well, they're slopes of tangent lines to the graph. All right, that's derivatives. Now, definite integrals, definite. All right, well, 1 second, folks. Let me spell that correctly. Definite integrals, what are they? Are areas under or below, or under or under or above. I'm sorry, folks. Whew. Where is my head? Under or above the graph. But you got to be careful. So the ones under the graph are with a plus sign, and the ones above the graph are with the minus sign. So, so I should call them signed areas. All right. So this is something that everybody should remember again from this class, even if you forget everything. And I know if I meet you 20 years later and let's say I ask you, so what do you remember from calculus? Maybe you don't remember much. Maybe you don't remember any of the formulas. But if you remember, folks, if you remember that derivatives, you know, oh, that's the slope of a tangent line, and integral, definite integrals, you know, areas under the graph. Well, that's already accomplishing much, because these are things that a lot of people seem to not realize, not to understand well, and then it becomes really difficult to understand, to kind of remember the concept. All right, so these are the main points of today's lesson. Now I'm going to do a bunch of calculations, and then we list some properties of these definite integrals, and that's going to be today's lesson. So, so I'm going to evaluate an integral now. All right, you might wonder, how am I going to do this? Well, pay attention here, because the secrets are going to be revealed in a few seconds. So we want to calculate this integral from 2 to 5, 4 minus 2x dx. How do we calculate that? Are we going to write that infinite sum and take a limit and such? No. Graphically, I am going to draw a graph of that particular function. And here's what the graph will look like. It's not so hard to do it, folks. We can do it with Desmos. I'm not going to pull Desmos right now because it's a bit, not so, well, you know what? Yeah, we could do with Desmos, but let's do that by hand. It's too easy to do that with Desmos. So let's say this is 2 and 5. Obviously, my scale is off here, but that's not the important thing. So let's see, what is this function that I'm looking at here? F of x equals 4 minus 2x. Remember, we look at the graph of that function, and I'm going to look at the graph of this function. And when x is 2, f is 4 minus 2 times 2, so that's 0. All right, and when x is 5, f of 2, folks, is 0, right? F of 5, because, we look at 2 and 5, these are the bounds. F of 5 is equal to 4 minus 2 times 5. 4 minus 10 is negative 6. So this function really looks like this. It's a line, obviously, everybody should remember at this point in time, you're in Calc 1, you really need to recognize the equation of a line, a linear equation, right? So there we go. So this point here is 5 and negative 6. So this is, folks, this is the graph whose area, this straight line is the graph whose area I want to calculate. The area above, right? So we know one thing, that this integral will have a minus sign. That's for sure. So it's going to be a negative number. What is this area, by the way? Can we calculate this area? Of course, this is a triangle, folks. So I know how to calculate the area of a triangle. And I'm going to say here, the base is 3, and the height is this one. It's a triangle with a right angle, by the way. Here, the height is 6. Right, so it's a 3 times 6 divided by 2. That's the area of a triangle. And because it's with a minus, we're going to say the answer here is negative 9, because 3 times 6 divided by 2 is 9. So that is the answer for our problem here. So we calculated that integral simply by looking at the picture. Now you might say, is this going to take us far in practice? The answer is no. But the good thing is that there are some situations when this interpretation is going to take you far, further than algebraic manipulations would take you, folks. And I'm going to do another calculation by again, manipulating the context here rather than doing anything, very intelligent. So I am going. Anything rather than doing an algebraic calculation. So number 22 is of the same form in a way. So you will see in a second. 22 from 4.2. So it says here, calculate the integral from 1 to 4 of x squared minus 4x plus 2. Now, I told you that in the previous problem, I could have used Desmos. In this one, I'm going to use Desmos. I don't like to graph things by hand a lot. So I have a function f of x equals x squared minus 4x plus 2. And I'm going to use Desmos to get me the graph of this particular function. So to use Desmos, all right. I am going